to call your attention to a conference that we will organize from 7th to 8th of November of this year in the University of São Paulo in honor of Professor Iberê Caldas, who is completing 70 years old, and many people who worked with him, collaborators, friends, and this invitation is being extended to all of you who would like to contribute. So thank you very much, and let's...
Okay, thank you, Ricardo. Our first speaker.
Can you hear me? Yeah?
Yeah. Kelly Iarosz, and she's going to talk about mathematical model of brain tumor.
Tá. Para poder ligar aqui. Obrigado, pode começar. Escolha que segue. Good afternoon, everyone. Thanks the organizer, and thanks everyone for staying here after lunch. Today, I'm talking about the mathematical model of brain tumor. For some person here, maybe this is strange because sometimes, did you see I talk about the plasticity? But during my talking, I connected this, and then you can understand why I talk about this model today. Here I put some names of the collaboration, but this collaboration is not just one collaboration. We have collaboration with these persons, these researchers. Started this in 2009. I am part of the Professor Iberê Caldas group in São Paulo University at the Institute of Physics, and the part of the 105 group size. Here we have some persons of this group, and in my last slide I pay attention of the names of the persons goes to the poster presentation and another speakers. And then properly I talk now about my talk. Sometimes we present about the brain and talk about the plasticity and different topologies and some neuronal models. Or we talk about the cardiac considerations, but today I'm talking about the lesions. The cancer or the tumors are maybe the main and more aggressive form of the lesions in our brain. And then we have some considerations about our cells. In some cases, we have a cell mother, and then this cell reproduced, separated. During this separated, we have cycle cells, and after the separation, we have a new two copies. But these normal cells can be divided around 50 times, one normal cells. When these cells suffer one deformity in DNA, these cells can be separated more times. But when this occurs, we have some deformations. And this deformation sometimes is called the cancer or tumor. We can separate this in begin, or we can separate it in malignant cancer or tumor. But the main case or the main consideration in this talking is we have the cell division. Our cell division is not normal. We have one damaging in this, and then we have a formation of the cancer or the tumor malignant. Here we have one short video about the metastasis. When the persons suffer this deformity in DNA, and then the cells goes to another part of the body. Normally, when we talk about the brain, we talk about the cells and goes from lung to brain. But our case is not this case, because this case is just the cells goes to the brain and then proliferation. In this case, we have just compression of the neurons. In our case, we don't use just the compression. We need to analyze what's happening with our neurons. And then this case of the metastasis is just one example from the lung to the brain. My talk is probably about this case. We have the glioma times the neurons. Why this? Some studies clarify the glia cells in the calling the name of the babysitter of the neurons, because the neurons have no property quality for providing nutrients or care for alone. And then who cares for the neurons? Glia cells. Glia cells are one class of the cells, and these cells can divide in another, but the main responsibility of these glia cells is care for our neurons, provide the nutrients, regulated our system, and what is important in this. I pay attention to this because if you have neurons, and here we have neurons, and then we have glia cells. These glia cells supported our neurons. Neurons cannot live alone. And then if your glia cells death, your neurons death. If you lost this support, our brain have some damage. And then here we have one example of the property case. In this case, we have one cut of the brain. And I know this picture is not so good, and the main now, because we lunch now. And then we have one cut. And this cut, we can look the proliferation of these glia cells. After this proliferation, some neurons death, and the part of our brain death, properly apoptosis, or necrosis, and some specific name for this. And then we have a part of our brain loose. We can discuss this in terms of the plasticity. We can conduct other discussions about the topology. But the main case is this lesion, this problem, this disease, case one damage in our brain. I can analyze the signals after this, or I can analyze what's happened with our new connections in this brain. But first, we need to know what's happening with the neurons and what's happening with our glioma or glial cells proliferation, and we have no treatment about this. Just put in this case and look for the ground. No, we have treatment. But the treatment is not so, the health is so soft. And then some perturbation in the system causes some effects. We have one specific form of the treatment, but not just this. We have another forms of the treatment. I pay attention to this, but we have more. Why I can pay attention to the chemotherapy? First, because the model is about the chemotherapy, and then first because of this. But the system of the health in Brazil offer sometimes this type of the treatment. And then what's the protocol for this treatment, this type of treatment? The person goes to the hospital or specialized clinics, and then wait one doctor and wait the protocol for drugs, for receive these drugs. And then the agent chemotherapy is infused in the person, and then the person wait. This, for us, we put some parameters in our equations, evaluated this in our computers, and they wait for our beautiful pictures. And then goes here and present some graphics. But the persons with the weight, these persons, it's calling them the so rude, so aggressive time for your life. And then some aspects are considered during this wait. Main, the hair loss. This is an effect more visible because the persons some persons, when you look for the talking, the persons have a cancer. These persons have no hair, or sometimes these persons have the ability of the face, the health. And this is because the infusion of the chemotherapy. The chemotherapy agent is aggressive for all the cells. Remember, I talked about if you have neurons, you have glial cells. These glial cells can be proliferation, and then we have one specific type of the cancer, called the glioma. The glioma can be attacked from the chemotherapy agents, but not just our glial cells. When you receive the chemotherapy agents, you receive attacked in your normal cells, in your glial cells, and your neuron cells. Because of this, we study during some years any considerations in cancer models. I would like to inform this. This is like my first love in science, because when I start my PhD, I studied this model. This is our first model I studied. And then in 2010, we studied about the suppression of the cancer, and then we can insert the delay in cells proliferation for consider the mutation. After this, you can insert the immune system and try to study what's happening with the immune system is fortaleced, because this is one type of the treatment. And then we study what's happening if we use the chemotherapy agents in pulsed infusion and continuous infusion, because we have these two types of the infusion of the chemotherapy. And then we study what's happening with the glia, neurons, and chemotherapy agents. After this, we study what's the relation between the dose-dense chemotherapy, because this is influenced so much. And then we study one phenomenon, clinical phenomenon, called the Norton-Simon hypothesis. And after this, we study the rules of this dose-dense chemotherapy. And this paper, this is our last paper submitted, is study the blood barrier in our brain. I call in pay attention to this because the José Trobia, where is the José Trobia, there one poster presentation about this paper. Then, okay, and then you can see in this timeline, we have some considerations about the mathematical models and the connection between the glia, neurons, and chemotherapy. Basically, our model show the neurons and the influence directed the glia cells in neurons. We have the competition between the glia cells and the cancer, because the glia cells and the cancer is connected. And then we have the influence directly in neurons, in glia cells, and the cancer cells when you put in your body the chemotherapy agents. This four equation represents our first consideration of the models. We have the first equation, and consider in this first equation the glia cells concentration. In second equation, we have a representation of the glioma cells. In this third equation, we have the neurons concentration in our brain. In the last equation, we have the concentration of the chemotherapy agent. I would like to show the interaction coefficient are so influent in our model. The proliferation rate are influent because we have, if you put the no realistic values in this model, we have no brain. We can insert some values and the simulated proliferation for all life. But if you don't limitate, you have one volume, a big volume. And in our brain, have no big volume. We need to limitate this. And then we have some consideration about the chemotherapy agents, because we try in our model the realistic drugs of the pharmaceutical industry. And then we try to use the drugs of the public system. And in my final slides, I show for you some considerations, because we receive this treatment, but this is not the best treatment today. But the public system offers this, and then you need to study what this public can be offered. Our results show the main results. I would like to pay attention to this. Treat one tumor is better than non-treat. This is not discutable. In this case, we have here one example. If there is no treatment, you don't insert any infusion of the chemotherapy agents in your treatment. Just wait the proliferation. And then when this occurs, the glioma grows, and then your glia cells down, because the glioma toms the volume of your brain. And consequently this, the neurons death. Remember, if you have no support, your neurons death. And then, if you try to apply the chemotherapy, for some time you receive the chemotherapy, the form continues, and then you can observe what's happening in your model. We have one evolution about the glia cells. We have the reduction of the glioma cells, and you have no neurogenesis of the neurons. And then you can remember the chemotherapy agents don't attack just the glia cells and just the glioma, attack to the neurons. But this loss of the neurons is not so aggressive like don't receive the treatment. And then we have here some considerations about remember about the volume of the brain. You need to put one limited of this, and then this is a carry capacity. It's like a density of our brain. Mass and volume, the reason about this. And then we have this constant, but it is represented, this alpha, represented the influence, how the neurons you lose inside of this volume, considering the carry capacity. And when you look at this, we can observe the best of the consideration of the treatment about the chemotherapy. In this case, we have here the color bar, and look the concentration of the neurons. In this case, in yellow, we have one reduction about the 2% of the neurons. And in this case, we have around 70% of the reduction of the neurons. In this green line, we have a mark of the alpha around the 2. And here we have the chemotherapy around the 16. Here is normalized model, but in real life, this is equivalent and 75 milligrams per liters of the infusion in your body. In this case, it continues. Imagine one person goes to the hospital, stay in the hospital, and then receive every day one infusion of the 75 milligrams for milliliters of the chemotherapy agents. And it is added today, and after this person receive, and after receive during the 1 month, for example. And the case of the health of the person decrease a lot. Because the cells of the body death, all the cells, the concentration of the cells death. And then, because of this, we consider this time space of the study. But I think the main results about this stay, this second, the figure 5, compared of these 2 lines. About time, because we have one first work and they explain about the suppression of the chemotherapy, the cancer, when you put one high concentration of chemotherapy or one low concentration. But the main study about this last figure stay here. When you infuse the chemotherapy and this is continuous, you have so damage in your body. You can kill the cancer cells, but you kill your body too. And then if you consider not just the infusion continuous, but you can consider one dose dense around the, this is the limitation of the pharmaco, this value, but during just 5 days. And then stop for 23 days, and the body recover your health, and then this body can be receive the drug now. But in this case, we have the regression of the glioma cells. We have one recover of the glia cells, and you have stabilized the neurons loss. But no, this type of treatment is not offered. Sometimes is not offered by public treatments. And then, because of this, I consider the last concluded reflections and pay attention of this conclusion about it. We have one model. We study about the type of insert chemotherapy. We know about the difference when you try the pulsed chemotherapy or the continuous. We know the main drug used in the normal treatments, but we know this is not the best. We have another types of the drugs, but it's not offered. This is just types of the offer. I remember this type of cancer is glioma cancer, and then is a specific drug for glioma. If you have interest in this and know more about why and about the carcinogenesis, you can read more about this in this paper. When you put in Web of Science, for example, this is one of the main papers about the explanations, because the cancer is not just the consideration about the external factors. And this is one attention. I remember, be careful with the news in our main journals like Facebook, because sometimes the news is not real. This is one example. This is permanecing the network during days. And some persons talk about the tumor necrosis factor in banana. This is crazy. If one person discover this, and then we can go to the Nobel for this person, because necrosis is factor of the human cells or the animal cells in some considerations, not the vegetative. And then, but this is a main information. The news in some network is banana has tumor necrosis factor. Eat banana like this with the spot, the black spots, because this is important, black spots. And then you can cure the cancer. But the original news is not this. It's one injection of the one specific drugs in rats, in mice, can be observed once some necrosis of the tumor in mouse, not in banana. And the banana is involved in extracted from banana. And then be careful with the news about the cancer and the same other diseases. Thank you very much. I would like to invite you to visit our website. And I would like to invite you visit the Trobia poster, the José Trobia poster, the Paulo poster, Paulo Protashevsky, and the tomorrow we have the talk with the Fabiano Ferrari. It's this. Okay, thank you.
Thank you for the nice talk. Questions? Comments? Questions? Ram?
Yeah. I was just wondering, how far are you from having clinical trials and the possibility of implementing some of these ideas?
And then we try the drugs and the actual protocols in the system of the health consider the pulsed chemotherapy. Yeah. And then but this is around 5 years ago. Just 5 years ago we started this. And the pharmaceutical industry use this some consideration. We have so many citations in our paper from 2015 doctors in medicine, in specific treatments of the medicine.
Trying it?
Yes, the community try to apply our model in your types of treatments. I wait, try more, but I wait.
Yeah. When you do these trials, as you're just answering, would you try to apply this model? It will be in the way the chemicals are used. I mean, do you need permission from Anvisa?
We have no tests in humans or rats or some cases. But if one doctor, one medical case goes to apply, and then he needs, yeah. But we don't need it because we take the data from another papers or the drugs tested from industry.
Okay.
Yeah. We try to use this type of the drugs for test our model first. And then we decide use one or two or three specific drugs. Yeah. Okay.
Thank you very much.
Thank you.
The next talk is not here, so we move to the following talk, and then we'll have a longer break for coffee. So the next speaker is Alexander. Alexander? Yeah. And he's going to talk about properties of liquid water from atomistic simulation and neural networks.
In the ribbon side. Yes.
Me sorprendía que no hacía ninguna pregunta. Estaba inquieta. Me dejas ahora más tranquila. Porque hiciste más preguntas. Yo decía, ¿qué le pasa a Ita que está tan callada? Ahora me quedo tranquila. Tenemos ayuda. Linda, siempre pregunta. Casi siempre pregunta. Por eso yo no me canso de preguntar. No me preocupa de preguntar nada. Yo ya cuento porque me vas a preguntar. Si no te vuelvo a pensar, ¿qué pregunto? Es interesante. Y si vos ya tenés que preguntar. Por eso, bueno, ahorrame el trabajo, dale.
Hi, good afternoon. Actually, I should know how to operate this because I'm from a local. I'm supposed to be a local. But anyway, first of all, I would like to thank the organizers for inviting me. I would also like to make a disclaimer that if halfway through the talk you realize or you think that this is completely off topic, you're right. I come completely from a different field, so I'm going to try to tailor my talk to this audience, and hopefully by the end you'll see something that is slightly related to dynamical systems and nonlinear systems. So what I do is simulations of atomistic simulations of solvated systems. So what I'm going to talk to you about is give you a slight motivation why we do this type of things. Then I'll go on to describing the type of systems that we actually simulate. And hopefully by the end, I'll show some results on simulating dynamics of water using neural networks. That's something that has interested us in the last few months. Okay, so the name of the game is sustainable and clean energy, albeit, the president of probably the richest country in the world and the president of this country do not really believe in that at the moment, but probably that will change. So the idea is to find new sources of energy that do not generate a carbon footprint. And one way of achieving this is by somehow obtaining hydrogen as an option, solar energy is another option, or combining this in different ways to obtain clean energy. And one way to do that is by electrochemical methods. So usually you have something inside a solution, typically a water solution, and you create reactions either by a chemical potential applied or by light. And you do chemical reactions inside this, and it's usually, a lot of the stuff is involved with breaking water. So water is really a key in all this, and although water is a very simple molecule, it's actually extremely complex to simulate if you want to understand its properties from a very fundamental point of view. And what I mean by fundamental is that you want to put all the electrons and all the interactions and do this as realistically as possible. So usually this is the type of device that I would like to simulate. So it's an electrochemical device. You have something like a water solution with probably salts inside. You have a cathode, an anode, and you apply a bias. You might also shine light to induce the chemical reaction. But let's keep light for the moment because the system is already complicated as it is. So really, what's happening here is that a lot of the stuff is actually happening at the interface between the solute and the solvent and your cathode or electrodes. So the surface between your system, your electrodes, and the solution is really playing a very, very important role. So that's what we would like to understand, is what is happening at this interface. So this is the typical problem that we would like to see. So we want to really put the atoms in the right places, particularly the surface and the water molecules. And this is already something that is very interesting because even depending on the type of surface that you have, you actually might see different effects. For example, in platinum, you can have either a hydrophobic or a hydrophilic surface just because of the orientation of your platinum. So platinum is an FCC crystal. Depending on how you cut it, you expose a different surface, so either a 111 or 100, and you can see that if you put like a droplet of water it wets the surface in a completely different manner depending on how you do it. So understanding this type of things is really important. So really the atomistic behavior on this structure is something that is important to see. Also, there's another ingredient, which is really when you put a battery. And then when you put a battery, something even more extreme might happen is that, well, basically, if you think about it, you're charging your electrode, so it's typically a metal. And so because you have charge and water is a very polar structure, then you should see some restructuring of the water on the surface. You might see some structuring. So even the water on the surface, which you might think that it's, it's a liquid or it has some structure, but it's a short-range structure when it's in the bulk. But when you put it on the surface, depending on the type of surface, you actually see structuring of water. And then if you apply a bias, then the structure actually might be changing. And so if you want to understand this, then the effect of the potential is also something that you need to include, right? So it becomes an extremely difficult problem to simulate. We need to do using high-performance computing. But basically what we want to do is to include quantum mechanical effects. So we really need to treat everything quantum mechanically. And that's what I'll try to argue with a very simple system. And then after that, hopefully, we can really obtain microscopic information to transpose it to the macroscopic effects. Okay, so how do we simulate this? So how do we model a problem like this? So, okay, the problem is a lot more complicated than this one, but this is the type of structure that we will simulate, and this is the best that can be done with a bias. So this is what we call the bulk water. These are electrodes. So in this case, it's gold, but it could be any metal or even a semiconductor. And we want to apply a bias between them. And there have been some proposals or some initial simulations on how to do this. You can use classical methods. And what I mean by classical methods is that somehow you propose a potential that describes the interaction between atoms or ions, and then you just solve Newton's equations using this potential distribution. And then what you do is you charge your electrodes to simulate a battery, and you see what are the effects of this type of systems. There also have been some attempts to do this quantum mechanically, so you solve a Schrödinger equation, or something that I will discuss a little bit in a few slides, which is called density functional theory. But you also simulate something like this. So you have water molecules explicitly. So all the atoms with all the electrons are described. And then you put it on a surface of a metal. So in this case, platinum, which is a very good catalyst. And then once you charge this surface here, then you want to understand what happens to, well, where do the electrons go, which is something that is very important, and you cannot do it classically, or what happens to the orientation of the molecules and how the dipoles of the water, which is really important for the electrochemistry, are reorienting. Okay, so essentially this is what we want to do. We want to do the dynamics of a disordered, very large system. This is our system. So in principle, we can do it using classical methods. And the good thing about classical methods is that you can do a very large number of atoms. You have to somehow parametrize the interaction between these atoms, and you have no electrons present. So if you want quantum mechanical effects, they're all somehow integrated out into this potential. And then you just solve Newton's equations of motion. Or you can do quantum mechanical methods, and by quantum mechanical it can be either really solving Schrödinger's equation by using what we call quantum chemistry, or we can use another method which is known as density functional theory. But the whole idea here is that you solve the quantum mechanical problem, and then the electrons are really included into your problem. The problem with this is that the accuracy is higher, but the number of atoms that you can calculate is much smaller, right? So if you really want to do a solution then this is kind of complicated to do. So what we plan to do is to find, well, the best of both worlds. So how can we get information about the local structure and then do something that we can build into a very much larger system? Okay, so how do we simulate this with a bias? And that's really a key here. And one way is actually to think about this problem in the same way that people have been thinking about it since the beginning of the century, which is, well, let's think about a problem where we have a molecule connected between electrodes, and this was very popular in the year 2000, and that's because the idea was to do what we call molecular electronics. Molecular electronics was the idea that you could use a molecule, a simple molecule, to substitute an entire electronic device, so for example, a transistor. So you imagine that you could actually do, information processing with a very small molecule composed of a very few small number of atoms. This obviously has to be calculated quantum mechanically. You want to see the flow of electrons across this device. And the whole thing is that we can do this. There's a theory to calculate this called non-equilibrium Green's function, because you see the system now, once you apply a bias, is completely out of equilibrium. There's no well-defined single chemical potential for the problem, right? So you need to do this out of equilibrium. It can be done. The whole idea then is actually that you have these electrodes. They're coupled to this region. Electrons are flowing from the left to the right. Well, depends on how you apply your battery. And then you have this region here which needs to be calculated quantum mechanically. So you need a quantum mechanical Hamiltonian, right? And this can be achieved by, so in principle what you have is you have a system of thousands and thousands, maybe millions of electrons. So it basically means that you have millions of degrees of freedom that need to be solved with a Schrödinger equation. So this is pretty much impossible to do. One thing to do is actually to think about the problem not in terms of a wave function, but you can actually solve the same problem thinking about of another quantity. So you can reformulate quantum mechanics in terms of the density, the electron density instead of the wave function. And this is why it's called a density functional theory. And for that one, you can actually write a mean field Hamiltonian known as the Conscient Hamiltonian, which is a single particle Hamiltonian for my many-body problem with the effect of a mean field potential. And so by doing this, we can actually have a Hamiltonian that has very small number of degrees of freedom, which is a mean field Hamiltonian that can be plugged into that non-equilibrium description, right? So from the non-equilibrium Green's function description, we have all the information about the non-equilibrium system. We have information about the density. We have information about the forces. And so we can do dynamics. So this we patched into a code a while ago. So we can do simulations of systems out of equilibrium. We can simulate molecular electronics. We can simulate devices in general. And we can simulate this problem because even though the system is out of equilibrium and you cannot use Hellman-Feynman's theorem, you can actually derive, starting from the momentum operator, you can derive a force for that particular problem, which falls exactly in the same functional form as the Hellman-Feynman theorem, as long as you are at steady state. And so here what we're going to do is actually to apply a bias which is non-time dependent. So the system there's no transient. We're just assuming that the system has reached the steady state. And then in principle, we can show that by calculating the force in the same way that we calculate using Hellman-Feynman's theorem, everything is consistent as long as we use the non-equilibrium density. So we're in place, right? So we can calculate non-equilibrium forces in a system. Sorry. Oh, okay, sorry. So this is what I'm going to show. So I'm going to rush through. The idea is that I will show you some results for this out of equilibrium systems. So for a very simple system, so we can do dynamics, but what I'm going to show is how the molecule on the surface, the water molecule on the surface, reorients due to this potential, and is actually coming not only from the fact that you have, well, you might think, okay, so I apply a bias, charge is accumulating, we have a capacitor, so charge is accumulating here, either positive or negative, depending on the bias. So, and the molecule is polar, so the molecule is reorienting solely because of this interaction between, you know, the dipole moment of the molecule plus a charge. Actually, what we find is that the molecule does reorient depending on the potential. So skip this part. So we look at how the molecule moves all around the surface. But the key point here is that as we apply a bias, depending on the bias, the molecule is actually different orientation on the surface. And this different orientation comes from the fact that you have a dipole. So there is a component which is coming from this interaction with the dipole. But there's also an effect that is known as Pauli repulsion, which is an effect that is fully quantum mechanical, and it's really coming from the fact that you have electrons on the metallic surface, you have electrons on the molecule. These two electrons have a wave function, and the wave function, because the electrons do not want to occupy the same state, it creates a cushion. So this is an indication that you have Pauli repulsion. Here is this density of electrons between the surface and the molecule, and this density actually changes depending on the bias. So basically means that if you apply a bias either positive or negative, this is actually trying to repel the molecule away from the surface or trying to bring it closer to the surface, right? So it's a combination of a classical effect and a quantum mechanical effect, meaning that you really, really need to include these things into the system to be able to simulate it. We can also do this for a single layer of water. So it also changes the frequency of the vibration. But the key point that I wanted to show is how do we take this into the next level, which is really simulating the full system. Well, what we can do is actually calculating these forces and obtaining these structures. We can feed this into a neural network. So we obtain the forces, the structure of the water on the surface or on the bulk, and then you can simulate the dynamics of water on a very, very large structure, including all the electrons, with the same accuracy as you would have for a fully quantum mechanical calculation. So this is what we do for bulk water. We do this using a deep neural network. And just to show you the results, so we do the convergence. So the forces are very small. We get energies which are of the order of micro electron volts. And the convergence is actually pretty good. And then we get the radial distribution, and you can see for our neural networks actually fitted very, very nicely with the DFT. The problem is that DFT has inherent problems compared to experiments. So our distribution is not as good as the experiments. So meaning that we probably need a better level of theory or better level of approximations within DFT to actually get the correct distribution of water, the bulk water. This is also seen, for example, in the self-diffusion coefficient. So this is not coming from our fitting, which is pretty good, but it's coming really from the structure that we use to fit. So the self-diffusion is actually off by a factor of 2, which is already pretty good. Compare that, the vanilla type of DFT, you get an error of a factor of 10. So just to finalize, the take-home message that we have here is that we have a force field that we fitted for this problem. We get a very good convergence, so we actually pretty sure that the DFT using this force field is actually pretty well fitted. And however, the underlying theory that we have is not probably good enough. So with this, I'll thank you very much. I'll thank my collaborators. And I'll thank you for being here, and all the people who paid the bills at the end. Thank you.
Comments? Questions?
Yeah.
Oh.
Do you think that any corrections due to bound states QED would be necessary in considering this?
Bound states in what sense?
QED? I mean, to describe the interactions at the surface.
Okay, no. No, one problem that we have is actually not QED. You don't need a QED to correct, but one problem that you have is that typically hydrogen, we consider the hydrogen as a point charge. So all the interactions are Coulomb interactions between the nucleus, so it's 1/r, and all the electrons. So now hydrogen is the mass is high, but it's not. But quantum mechanical effects of the distribution of the nucleus is somewhat important. So we will actually planning to include also effects coming from nuclear effects. That's something that needs to be accounted for.
I have a question. You described, of course, the DFT and the whole quantum mechanical thing, but how good are methods like yours, like the ones that you're using with the neural networks, using purely classical trajectories? Supposing you're just doing a set of equations.
Yes. So I would say in this form. So the force field is as good as your underlying fitting parameters. So provided you have enough layers, provided you have enough input and enough frames, you will get as good as your sampling space. The problem that needs to be addressed is whether the classical methods include all the effects for something that you have not simulated. Because typically what you do is you simulate a very small problem, and then you fit a force field, a classical force field for that particular problem, but it's not necessarily transferable to all systems. I'll give you an example. So if you want to simulate benzene, then you do a calculation for benzene. And then you have a force field for carbon, you have a force field for the hydrogen. Now, if you want to simulate purine, which has a nitrogen, then the carbon that you have interacting with the nitrogen is a different carbon than the one interaction with nitrogen. So for these classical force fields, you have different carbons, which for practical purposes is good, but from a kind of physical point of view, it makes very little sense. So that's why the idea is actually to skip the idea of a classical force field and go directly from DFT to a neural network that will provide you with a force field. Because then basically what you're trying to do is to get as much of the sample of the phase space as possible so that you don't have to write down a force field, an explicit force field. It's all contained in the neural network.
Okay, listen to the speaker and the two speakers. Poster session, and we back at 4:30.
You chair the next session. You're chairing the next session.
I'm chairing.
Just check here.
Good.